Hello and welcome back to Dynamic System Modeling. We will continue our discussion on the block diagram or a Simulink model. And we mentioned previously that Simulink model is a powerful tool for solving mathematical models representing a physical system. So by using the block diagram or Simulink model, we will be able to evaluate the response of the system under different input functions, and this could be done at high precision and at high speed. So we will be given a system like this physical system. This is a toy train. Okay, we need to convert this into a differential equation, into a mathematical equation that describes the system, and then this differential equation can be evaluated or solved using the block diagram model. So the first step in the modeling process is that we should be understanding this system, okay? And the toy train is made up of a locomotive, which is the mass of the engine, M1, and the trailer, which is the mass of the car, just attached to the locomotive. And those two masses are coupled together with a stiffness K. And of course the engine is exerting a force F of t, and the train is moving to the left. The friction between the wheels and the track is denoted by mu, which is the rolling friction or rolling resistance. And the total force or total coefficient of friction can be determined using Coulomb laws, which is P1 equal mu m1g. Remember, this is the normal is equal to the normal is equal to the weight, right? And from this we can determine the Coulomb coefficient. Now the first step in the modeling, we should denote the reference. Okay, this is x1 and this is x2. Second step, we draw the block diagram. The force of engine exerted on the engine of mass m1, friction, the D'Alembert law, and the force of the coupling between the spring between the two masses, okay, which is equal to k x1 minus x2. For every action there is equal and opposite reaction, so the force is in the opposite direction of the same magnitude. Okay, we have a resistance and the D'Alembert law m2 x2 double dot. After having the free body diagram, we can write down the differential equations. So having those two differential equations can describe clearly the physical model. So it's easier for an engineer to handle the mathematical equation than handling the physical system itself. Right? So the next step after having those two differential equations, now we want to analyze it. Okay, we need to solve those equations, and this can be done using Simulink model or block diagram model. So the first equation, we can see that we have x1 double dot and x1 dot and x1. And of course, if we integrate x1 double dot, we can get x1 double dot, x dot and x1. So what we can do, we can have x1 double dot integrated, get x1 dot integrated x1. Similarly, now we want to determine x1 double dot. x1 double dot is equal to what? x1 double dot is equal to 1 over m1, you can open the bracket, minus p 1 x1 dot minus k1 x1 minus x2 plus f of t. Okay, so x1 double dot is made up of summing three elements, so we need a summation term, okay, or summation element, okay, in which we have minus p x1 dot, k1 x1 minus x2, we can get x1, subtract it from x2, multiplied by k1 minus plus f of t. The summation of those three elements are multiplied by 1 over m2. So we need again a gain, 1 over m1. Okay, similarly we can determine x2 double dot. We have minus p2 x2 dot plus k1 or kx1 minus x2. We can get this term directly plus, and those two elements are multiplied by 1 over m2. This train is a toy train, and we are given that m1 is equal, the mass of the engine is 1 kilogram, the mass of the trailer is 0.5 kilogram, the stiffness between the two masses is 1 Newton per second, and this is not 1 Newton per second. Okay, this must be meter. Okay, sorry. And the force 1 Newton. Okay, the mu 0.02 second per meter, and this is the gravity 9.8 meter per second squared. Alright, now we have MATLAB. We can go to Simulink library, have a new model, and from our modeling we have the integrators, we have a summation term, and we have the gains. Okay, let's add them. So we have the integrator. You can hold the control tab in order to have multiple objects of the same element. Control R. We can go to math operations. We have the add, Control R, double click, minus, apply, okay, which is equal 1 over m1. Okay. Let's zoom in order to see inside the block. So this is x1 dot, double dot, x1 b dot, this is b1, so now we can go to sources, signal generator, this is f of t. Okay, we will be inserting square minus 1, and the amplitude here we put as minus 1 is positive amplitude, steps negative before stepping positive, and we will be using the frequency 0.01 hertz. Okay, apply. Now we want to observe the output. You can go and have this code from the sinks. Okay, so we are interested on what? Dot, and we may be interested on looking over the displacement of the cart and displacement of the trailer. This is x2, x1. Okay. Now we must define the different parameters. One, kilogram. Mass to M2 is equal to 0.5 kilograms, and K is equal to 1. Force is equal to 1. I mean, we already defined it, no problem. Mu is equal to 0.02, and the gravity is equal to 9.8. So then B1 is equal to mu multiplied by M1 times gravity. B2 is mass 2 multiplied by gravity and mu. We can go run the model, change the model configuration parameters either okay from this side, in which we can extend a little bit the time, and okay, sorry, and the stop time can be changed into 1000. Okay, or it can be changed from here. Okay, now we can run. We have x1 dot. We have x1 the displacement, and we have x2.